Good afternoon, everybody. Welcome to a fun-filled afternoon of Chem 170 with your host, me, Dr. White. Hi, everybody. I hope you're having a good day. I am. Any day I get up and I'm breathing, that's a good day for me. I'm one of those half-filled, not half-empty persons. All right. A week from today will be test number 2. If you go to D2L, and also you should have gotten an email on Wednesday, 10/13, I will give test number 2 online, and you'll be able to download a password protected file for test number 2 from the assignment area on D2L. And that will be available next Tuesday afternoon. At Wednesday at 4 p.m., maybe even a little earlier, I'll send out an email via email the password for test number 2 PDF file. You'll have until this, I've got to change. That should be Thursday. Made a mistake. I'll change it later today. You'll have until Thursday, 10 a.m. to finish test number 2 and upload it. Your test number 2 answers to D2L, the assignment area. Should take you about 40 minutes, but if you need an hour or a little more, that's okay. Test number 2 has 9 pages. There are 10 problems. Some of the problems are multiple part. I never in Chem 170 have and will give a multiple choice question, period. It will cover alcohols, thiols, ethers, ethylene oxide reactions, and aldehydes and ketones. For test number 2, there'll be 11 points general knowledge, 34 points nomenclature, and 60 points reactions. And if you notice, that adds up to 105. So there's 5 bonus points. And like all tests, this will not be open notes or open internet. I have things I put in there that I can tell if somebody does that, and I'll do what's in my syllabus if I think you've done that. And next Monday, I will do a review for the material on test number 2. I'll do my world famous review for next test. On the Wednesday of the test, the 13th, we still will have our regular Zoom meeting for lab and other material. And as always, gang gesund. Any questions about test number 2? Speakers on. Early on when I started doing Zoom, I can't hear you. What did you say? I forgot to turn my speakers on. I have huge speakers over my monitor amplified, so I don't have to wear my hearing aid. All right. Well, let's go move on. On Monday, I just started talking about the Grignard reagent created by the great organic chemist, one of my heroes, Victor Grignard. And Dr. Grignard found or discovered or created that when you react an alkyl halide, where X can be chlorine, bromine, or iodine, with magnesium, you get the Grignard reagent. And remember that R is bonded and the X here to the halogen is now bonded to the magnesium, and the halogen is bonded to the magnesium, not the other way around. This is wrong. It even says it on the screen. All right, let's have some fun making the Grignard reagent. And since I already did this, it's your turn. what would be the organic product or products for the following? 3 points each. And when you're done, don't forget, give me a thumbs up. And for those who finished early, please be patient. I do try and give everybody time to finish. Come on, finish. All right, I think everybody's finished. Let's take a look at this reaction. And the question is, look at an organic molecule and look for what's different. What's not a carbon-carbon single bond or carbon hydro? Ooh, halogen on a carbon, that's an alkyl halide. Plus, that's your not carbohydrate, magnesium. And what you get, remember, X can be chlorine, bromine, or iodine. And what you get is the Grignard reagent. And remember, do you break carbon-carbon single bonds? No. So I have right here 4 across. I better end up with 4 across. And on the carbon with the halogen will be now magnesium. And bond to that is iodine. And I know there are 4 bonds to carbon. So I can do this. And that's how you do it. And on test 2, unlike test 1, I will have either 3 or 4 synthesis problems. So let's try one. And the question is, what would I react with magnesium to make that molecule? Your turn. And when you're done, don't forget to give me the signal. All right, I think everybody's done. So I better get to work. Now, if we look at the product, what we're making, look for what's different. What's not carbon, what's not, whoa, magnesium chloride and a carbon, that's a Grignard. Remember, X can be, in this case, it is chlorine, bromine, or iodine. And this is my R group. And what do we start with to make a Grignard? An alkyl halide. And what's my X? Well, we know that it's chlorine. So my R group is this. The carbon with the Grignard, magnesium chloride, is the carbon the halogen is attached to. And there you go. Now the question is, all right, we made it. What's the big deal with the Grignard reagent? And also, what was the reason this reaction, also a couple others, but mainly this reagent allowed Victor Grignard to win the Nobel Prize in the 1910s or 1920s somewhere around that time. Well, let's find out. This is why. And that's the Grignard reaction. And the Grignard reaction, in this case with ketones and aldehydes, if you take a ketone or aldehyde, if R prime can be carbons or hydrogens. If R prime is hydrogen, it's an aldehyde. If it's carbons, it's a ketone. Now, one thing I haven't done before, and I better explain. Organic chemists are lazy, and what this means right here is first I react A with B, and whatever I make, I then, second step, react it with C, and what I make overall is D. So this is a shorthand that organic chemists use. We're lazy. Instead of writing two separate reactions, we just do this. And therefore, again, what this means is I take A, react it first with B, and then whatever I get, the second step, I react with C, and my final product is D. So in the Grignard reagent, first reaction, you take an aldehyde and ketone and react it with the Grignard reagent, and then the second step, acid and water, and what you get, first of all, is an alcohol, but what's most important, and notice I have R triple prime here, you make something very rare, very special, a carbon-carbon single bond. Of all the hundreds of reactions I personally know, and there are many more I don't know, there are only a handful, like 20, give or take a few, where you can make that very special, rare thing, a carbon-carbon single bond. And when you do, it's good, it's fun, and it's very important. So let's look at the Grignard reaction. Now, what I'm going to do right now is a mechanism. I haven't done mechanisms because we just don't have the time, but I'd like to do it here. And H plus, remember, is acid, like sulfuric acid you'd use. Remember, right here, we've made that special thing, a carbon-carbon single bond, and the carbonyl carbon is this carbon of the alcohol. Now, a carbonyl again switches off for this is slightly positive carbon, slightly negative oxygen. And you can think, and I'll use quote, think, a Grignard is R minus. It's not really, but you can think of it as R minus MgX plus. And this is called a carbanion. And carbanions are very, very reactive. They don't want to be like that. Carbon does not want any kind of negative. And what happens is this will attack the carbonyl. So first step, this attacks the carbonyl, forms a carbon-carbon single bond, and you form this the carboxylate anion of an alcohol. This is a strong base, real strong base. And a base is something that accepts the protons. And second step, acid and water, you put a proton on here, this, and make the alcohol. That's just an acid base. Again, this is never going to be on a test, but it helps you understand what's going on. Now let's do one. Wonder why I was writing on an angle. My tablet wasn't at the right angle I normally keep it. Now I should straighten things out. And the question is, what do you make? And I'll do this one. You know, I'm going to let you have fun with this. I'll share. But what's different here? Ooh, carbonyl with hydrogen and carbons. And that's an aldehyde, but it could have been a ketone. If R prime is H, which it is, it's an aldehyde. Then what's different here? Carbon, magnesium halide, a Grignard. And remember, X can be chlorine, bromine, or in this case, iodine. And second step, acid and water. And keep your eye on the carbonyl carbon. That's where the fun is. What's attached to it is still attached. You don't break carbon-carbon single bonds. And then this opens up to an alcohol. And now, oops, I forgot to do this. You form that special thing from the Grignard, a carbon-carbon single bond. So what's our prime? H. What's our double prime? Ethyl. And what's our triple prime? Ethyl. So I'm going to keep my eye on this carbon. I'm going to write that first, which is this carbon. What's attached to it? R prime, H. Our double prime, ethyl, 2 carbons. This becomes an alcohol. That's what this shows us. And then to that carbon, my Grignard. What's our triple prime? Ethyl. And in one step, we've made a much more complex alcohol, which I can use to make things with. And I've used Grignard reagents in my PhD thesis. In industry, the areas I worked at, we haven't, but it's still awful, beautiful, great reaction. All right, I'm going to let you have some fun. And the question would be, what are the organic product or products for the following reaction? Now we're getting in some real fun reactions. Dr. White's happy, beyond happy. Remember, now you're on my home court. Ketones and aldehydes are my favorite. There's another one I'll get to also that's my favorite. Only because it helped me make a lot of money. That always makes something my favorite. Thank you, Megan. Thank you, Tim. And it looks like Calvin's finished and Emily, assuming you're finished too. All right, let's look at this reaction. Again, identify what's different. Ooh, oxygen double bond to carbon, carbonyl. It's got carbons here, R prime, carbons here, R double prime. It's a ketone. Now, it could have been an aldehyde. And then I look here, carbon, magnesium chloride, second step acid water. That's a Grignard. Remember, R prime, R double prime, and R triple prime are like X, Y, and Z in math, just variables in organic. That means stuff with carbons and hydrogens. And second step acid and water. Keep your eye on the carbonyl carbon. What's attached to it, R prime or hydrogen, R double prime. This carbon becomes an alcohol. And now from the Grignard, you do that special thing. You make something very rare and very powerful, a carbon-carbon single bond. So if I look up here, there's my R prime, there's my R double prime, and this is my R triple prime. Here's my carbon here, which is this carbon, which becomes this carbon. So I'm going to draw that. What's attached to it? R prime methyl, R double prime. I have my alcohol. And what's my R triple prime? Methyl. And now I've made a very complex tertiary alcohol. I'll talk about it later in another chapter, but various alcohols are useful to help you make, are you ready for this? Perfumes. One of the most complex and lucrative parts of organic chemistry, besides medicine, making medicine, is perfumes and also other cosmetics, but perfume is extremely lucrative. Oh, this was fun. I've got to do it again. And here's one for you to try. What would be the organic product or products that will follow it? Oh, that would be a fun reaction to do. Thank you, Megan. Got some nice trees behind you, or those bushes.
They're oak trees.
That's what I thought. I wasn't sure. All right, anybody need more time? I think everybody's done. So if we look at this, the starting material, what's different? Oxygen, double bond to carbon. Carbons here, carbons here. It's a ketone in a ring. But it could have been an aldehyde, but it's not. It's a ketone. And R prime and R double prime are just part of the ring. Next, carbon, 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 magnesium bromide. That's a Grignard. Remember, X can be chlorine, bromine, or iodine. And second step, acid and water. H plus is acid, H2O, I hope everybody knows is water. And now keep your eye on the carbonyl carbon, IM. And what's attached to it, our prime or H, our double prime, is still there. This becomes an alcohol. And now, oh, I forgot to put my triple prime. And now I do something very special, very rare. I make a carbon-carbon single bond from the Grignard to the carbon that was the carbonyl carbon. So if I look up here, my whole ring is R and R prime. You don't break carbon-carbon single bonds, so the methyl group comes along, both of them. This carbon right here is this carbon right here, is this carbon. So it's going to have an alcohol or hydroxyl group. And then what's my R triple prime? My isopropyl. The carbon with the halogen or with the Grignard is the carbon bonded to this carbon with the hydroxyl group. In this case, the center of 3 carbons. And having a simple ketone, a very simple Grignard, I've made a very complex molecule. Now, even if there weren't methyl groups on there, to make something like that, I don't know how to simply make it. It would be quite challenging for me to make that without the Grignard reagent. With the Grignard reagent, it's a piece of cake. By the way, let me show you something, switches off. How would you do this reaction? Well, one of the things you would need would be this Grignard. And what I'm going to do now, I'm just showing you how an synthetic organic chemist thinks. I need this Grignard. Well, what would I need for that? Well, I need this alkyl chloride. And how would I make that? And these are all reactions I've taught you. And that's how an organic chemist works backwards to say, if I can't buy this, I really can't buy this cheaply, but I know I can buy this cheaply. And let's assume for today's class, you could buy that ketone. Well, that's how an organic chemist, synthetic organic chemist thinks. Yes, that's going on in my brain. Uh-oh, you better be careful. All right. Important thing. As of today, the Supreme Court has still outlawed cruel and unusual punishment to students, at least as of today. And I will never put a Grignard synthesis problem on a test or the final, because that definitely would be cruel and unusual punishment. But you should know how to take a ketone or aldehyde and a Grignard reagent, second step acid and water, to make that very special thing, a carbon-carbon single bond. Very rare, very special, very powerful. Allows organic chemists to make things we normally couldn't make easily. And that's one of the reasons Victor Grignard won a Nobel Prize. It's a good reason. All right, let's move on. Now, let's talk about reduction. Reduction is when you change the oxidation state, but it's still called reduction of carbonyl compounds. And let's talk about hydrogenation. Now, if we look at a ketone or aldehyde, which just so happens to be on the screen right now, I should have had an H here. I have a carbon-oxygen double bond, a carbonyl. And what is that? That's 1 pi bond and 1 sigma bond. Oh, you know pi bonds from a carbon-carbon double bond. And if I add hydrogen and a catalyst. And the catalyst, guess what, can be nickel, platinum, or palladium, which you've learned before. I break the pi bond, but now each atom of the double bond, oxygen and carbon, gets a hydrogen. And what have I made? An alcohol. So if you take a ketone or aldehyde, hydrogenate it with a catalyst, you'll make an alcohol. So let's take a look at that reaction. But first, if you're writing it down, I'll give you time-wise to have some water. And remember, Dr. White has the fastest mouse wheel and also mouse left click button finger in this side or the other side of the Mississippi. If you want me to go back to the slide, ask, and I always will. If we look at the following, the question is, what's the organic product or products for the following? I'll do this one. And the question is, well, what do we have that's different here? Ooh, carbonyl with carbons here and here. It's a ketone. Could have been an aldehyde, but it's not. I'm reacting with hydrogen, H2. And what's this Ni? It's a nickel catalyst. By the way, when I worked at a company, we did reactions like this. Usually we use Harshaw's 5132P, which is a special type of nickel catalyst. Don't ask me why I still remember that. I used it enough times, that's why. But remember, a catalyst can be nickel, platinum, or palladium, because the cost usually, unless you're in the pharmaceuticals, you don't, or research at a college, you don't use platinum or palladium. You stick to nickel cost-wise. And what happens is what's attached to the carbonyl carbon is still attached because you don't break carbon-carbon single bonds. You break the pi bond here, and each atom of the carbonyl carbon oxygen double bond gets a hydrogen. So here's my R prime, here's my R double prime, here's my carbonyl carbon. What's attached to it? My R prime methyl, my R double prime. And then I'll have each atom of the carbonyl carbon oxygen double bond gets a hydrogen. I've made an alcohol. And I could write it another way if you wanted to on a test. These two are identical molecules. I've just kept the bond angle there from the carbonyl, which organic chemists tend to do. We're lazy. All right, time for you to have some fun. And there you go. If you react that with hydrogen and platinum, what would be the product or products you get? Remember, these are the ways we make building blocks or actual products we use, or you use and I use, I guess we use in our daily life. And don't forget to give me the secret signal when you're done. Thumbs up. If you have anybody walking behind you, say hello from Dr. White. All right, looks like everybody's done. And what do we have that's different here? Ooh, carbonyl. Carbon double bond to oxygen. What gave it away? Oxygen. And on there is a hydrogen. Could have been an R group, but it's a hydrogen. R prime is hydrogen. I have carbons here. I'll call R double prime an aldehyde. I'm reacting with hydrogen gas, H2. What's platinum? A catalyst. And remember, the catalyst can be nickel, platinum, which we are using today, or palladium. And what's attached to the carbonyl carbon is still attached to our prime or hydrogen, our double prime. And you break the pi bond. There's one pi bond there. And each atom of the carbonyl, carbon oxygen double bond, gets a hydrogen. So if we look at this, here's my R double prime, my R prime, I'll call hydrogen. Keep my eye on the carbonyl carbon. I'll draw that first, which is attached to it, R prime hydrogen. Then my 4 carbons like this. And then I'll write it the lazy way. Each atom of the carbonyl gets a hydrogen. I know there are 4 bonds to carbon, and I can fill in the rest. And notice what I did here, gave you a big scary molecule, which is not big and scary if you know how to look at it. Oh, let's do another one. These are exciting. What would I react with hydrogen and catalyst to make that compound? And this I can put on the test as a synthesis problem. Psst, you're doing organic chemistry. Hopefully it's not too painful. Yeah, is everybody done? I think so. Don't forget to give me the thumbs up. When I'm in a classroom, I can look around, see if people have stopped writing. Usually I'll give me that look like, get to work, Dr. White. Or I'll ask, when you're done, look up and smile. All right, let's get working. If we look at the product, what's different? What's that carbon? Hydrogen, an oxygen with a hydrogen on it, on a carbon, that's an alcohol. I'm going to write it like this. And what's attached to it? Carbons here in the ring. This so happens R prime and R double prime are connected together. This could be a hydrogen, but it's not. And I have H2, what's palladium, a catalyst. And remember, catalyst can be nickel, platinum, or in this case, palladium. And what do we start with? an aldehyde or ketone. So the carbon with the hydroxyl group is the carbon double bond to oxygen, the carbonyl. Remember, carbonyl group, carbon, oxygen, double bond. So here's this carbon right here, which is this carbon, which will become this carbon. So it's attached to it. Will still be attached to it. We're talking about this carbon right there. And now I'll draw my double bond to oxygen, and that's the product. And that's how you do it. All right. Now, I'm going to write something down to whiteboard. Do not copy it unless you want to, but you don't have to. What if I want to make this alcohol from this aldehyde? Let me rewrite this a little different. This would be CH2, this would be OH. Well, you say, oh, I know what to do. I'll add hydrogen to catalyst, nickel. And right here, that would be that. But oops, what do we have here? A double bond. And you learned that H2 and a catalyst, where the catalyst can be, in this case, nickel, platinum, or palladium. Again, you don't have to write this down. You break the pi bond, and each carbon gets a hydrogen. So you're not going to get this. What you'll probably get is a mixture of things, but probably one of the things you'll get, which you don't want, is this. But I wanted to keep that double bond. Well, I can't do it this way. How can I reduce that aldehyde to an alcohol? Well, it turns out in organic chemistry, these type of problems happen. And turns out there was a great, I don't know if he's still alive, I don't think so, a great organic chemist, Dr. H.C. Brown, Dr. Brown from Purdue University, and at the end of World War II, came out with two new reagents, which he invented, and he won the Nobel Prize for that too in the 1970s. Why it took so long was a disgrace, really, but that's another story for another day. And the reagent I'm going to teach you about is lithium aluminum hydride. Lithium aluminum hydride is LiAl, lithium, LiAl, aluminum, then hydride, 4 hydrogens. And it's a nucleophile. Think of it like a Grignard, but instead of R triple prime, you have H minus. And the H minus attacks that, and you make this carbon hydrogen bond. It essentially does the same thing. However, lithium aluminum hydride will not react with a carbon-to-carbon double bond. So if the reaction I showed you before, if I had used lithium aluminum hydride, it would have worked to give me the product. So let's take a look at this. How are we doing time-wise? Doing good. Again, I'm going to use the methodology, first step, I'll react it with a lithium aluminum hydride. And second step, acid and water. And this is similar to what happened at Grignard. You make an alkoxide, then you acidify it. That's what H+ in water is called. And what's attached to the carbon, let's take a look at this first. What would be the organic product or products of this? What's different here? Oxygen, double bond to carbon. Carbon's here on this carbon, and carbon's here. Now, could have been a hydrogen, an aldehyde, it's not. Again, first step, lithium aluminum hydride. Second step, acid and water. And what's attached to the carbonyl carbon is still attached. You break the pi bond, and each atom of the carbonyl gets a hydrogen. Well, this is my R prime. This is my R double prime. Here's my carbon that came from the carbonyl. So I'm going to write that first, and what's attached to it is still attached, because you don't break carbon-carbon single bonds. They just come along for the ride. And then this carbon will have an oxygen, and each atom gets that. So if you have your ketone, you need an alcohol, you can use this as opposed to hydrogen, a catalyst. And in my research for my PhD thesis, I did use this reagent and this reaction a number of times, and it works good.
Can you go back up for like 2 seconds, Dr. White?
Do what?
Just scroll back up for like 2 seconds.
How about 7.5 seconds? Tell me when you're done.
Okay, I'm done. Thank you.
Aren't you glad I gave you more than 2 seconds? I will always do that. Oops. And why don't you do the following reaction? What would be the organic product or products of the following? I keep on looking at all of you who have your web camera on, and like this semester, last semester, I had 2 students with their dogs would join us during the class. I always ask them, have your dog wave to us? And they did, with help from their master. And thank you, Megan, and I'll wait for everybody to be done. Get done. And is everybody done? Thank you. All right, let's take a look at this. What's different? Ooh, oxygen, double bond to carbon, hydrogen, but it could be R prime, or it could, in this case, this hydrogen. Carbon's here. And we have up here an aldehyde. It could have been a ketone. React it with lithium aluminum hydride. Second step, acid and water, acid H+. Keep your eye on the carbonyl carbon. What's attached to it? Still there, break the pi bond. Each atom of the carbonyl carbon double bond to oxygen gets a hydrogen. Here's my R prime. Here's my R double prime. Here's my carbonyl. I'll write that first. R prime hydrogen, R double prime. And now break the pi bond, and each atom of the carbonyl gets a hydrogen. Does everybody see that? Does everybody know the significance of this reaction? Time's up. What did you make? Well, I'm going to rewrite this way. What's that? Ethanol, which is the key ingredient in vodka and other things. And this is probably the most expensive way I know to make ethanol. You never would want to do this. It's way expensive. And with that, I've gone a little over. Let's take a 5-minute break, come back at 1:57. That's when your digital watch says 1:57. Let's see, have military time. And I'll see you in 5 minutes. Oh no, I'm running late. All aboard. We're moving out of the station. All right. Welcome back. Sorry, Bob. Oh no, a whole almost 60 seconds late. Wait. All right, before we move on, it's time for a public service announcement from Dr. White. When you drove by a gas station or went in one, did you happen to think that gasoline contains ethanol, which is an alcohol? Did you happen to look at a bottle of rubbing alcohol and see it has 2 propanols? That's never going to be on the label. The common name, isopropyl alcohol, and water, and that's an alcohol and rubbing alcohol. Did you do that? How about, did you happen to look at nail polish remover? Notice I took off my nail polish. No, I don't put any on. Did you happen to look at a bottle of nail polish remover and see that has acetone in it? Mainly acetone with a little perfume. And acetone is a ketone. Did you do that? I don't know. Remember, organic chemistry is all around you, and won't hurt to think about it when you're not in lecture with me. It's all around you and it's fun to think about. So I highly recommend you do. All right, the next section we're going to talk about, oh wait, what was I should finish this one up. Let's do one more of these. Remember, on test 2, I'll have a couple of synthesis problems. So what would I react with lithium aluminum hydride, first step, second step, H plus acid and water to make that molecule? Right now, I'm secretly training you to be synthetic organic chemists. Not really, but it sounds good. Uh-oh. I think I have a corrupted file I got to track down. Hang in there while I close everything and reopen my Word. It only happens with Word. All right, sorry about that. I've been meaning to call my computer guy and ask him, A, do I have a corrupt file, or do I have to add more memory to my machine? Because I am doing a lot right now doing this. All right, let's get back to work. Question is, what do you start with to react with lithium aluminum hydride and acid and water, second step, to make this compound. Well, I have lithium aluminum hydride. Second step, acid and water. And what's different here? Ooh, hydroxyl group on a carbon, and that's an alcohol, which I'm going to draw it this way. And this carbon is this carbon. If we look at this, one of these is R prime. This, which is attached to that carbon, I'll call R double prime. And what do we start with? A ketone or aldehyde. Now, in this case, are we adding any carbons? No. So if we end up with 4, we better start with 4. And the carbon with the hydroxyl group is the carbon double bond to oxygen. And then notice R prime is a hydrogen. And I know there are 4 bonds to carbon. And this would be the starting material. And if I did this reaction, what would I get? This, which normally I would write like this, but I'm training you now to look at also this. And this and this are the same. I just moved these two to H2. And that's how you do lithium aluminum hydride. All right, we're getting to a very special part of this chapter, this course. And this deals with something called enolate anions. I have to admit up front, my PhD thesis dealt with a very specialized enolate anion, and I'm a world authority on enolate anions. And in fact, if I were to tell you what it is, which I will do later, most chemists at ECC don't know what the heck I just said. But anyways, some of the slides here are going to be click off position. I won't ask you questions about it on a test, but this is important background information for you to understand what I will talk about. All right, when we have a ketone or aldehyde, we have what's called keto-enol tautomerism. Tautomerism are 2 different structures that only differ by the placement of a hydrogen and carbon-carbon bonds. So these can exist in equilibrium in 2 forms. One's called the keto and one's called the enol. See board for something, so I better get to work. That's not what I wanted. Now let me write, it can be more complex, but I'll just write it this way. Again, switches off, but this is important background information. Here I have an aldehyde or ketone. If R prime is hydrogen, aldehyde. If R prime is carbons, ketones. Now, here we have the carbonyl carbon. The carbon attached to that has a special name. And that's called the alpha carbon. I'll never ask this on a test, but I'll be talking about it. And this is the alpha carbon. And if we have a keto-enol tautomerism and equilibrium, the hydrogen here goes to the oxygen, double bond moves over here. Again, this you don't have to write down. This is called the keto form. This double bond, ene, alcohol, OL, and that's called the enol form. And because a ketone or aldehyde can be in equilibrium like this, this has important implications to the acidity of the hydrogens on the alpha carbon. The hydrogens on the alpha carbon are acidic, which means you can pull them off with a weak base, unlike CH2 in a normal molecule, which are not acidic. Oops, and as I said, it's also the hydrogens on the alpha carbon in a ketone or aldehyde are called the alpha hydrogens because they're on the alpha carbon. By the way, in case you don't know, this is the Greek letter alpha. I was in a fraternity, and as a pledge, one of the things the pledges all had to know and memorize was the Greek alphabet, alpha, beta, gamma, and so on. And that's alpha. By the way, I hate to see it on TV where a lot of people are protesting fraternities on campuses. And throughout the years, even when I was an undergrad, they're good fraternities and bad fraternities, just like they're good people and bad people in life. I was in a good fraternity. We never did bad things to people. We had wild parties. Oops, I shouldn't talk about our toga parties. Oh, hold on. Do I have time? Yep. I'll just say something real quick. How many of you seen the movie Animal House? If you haven't, watch it. Animal House was written about my fraternity, not the whole fraternity, my actual chapter when I was there. Yeah, I got time for the story, and I won't even cut this out of the video. Back when I was a freshman, I was rushed by a fraternity, Alpha Epsilon Pi, at IIT. It's no longer there. A couple of fraternities have died at that school. But anyways, they're chapters, I should say, Lambda chapter. And my semester, when I was rushed, was the first time the school allowed fraternities to take pledges off campus for rush week. So on Tuesday of rush week, Alpha Epsilon Pi, all the rushies, people they wanted to pledge, plus the brothers, about 100 people in total, big group, we went to Second City in Chicago. I don't know if you've ever been in Second City in Chicago. I haven't been there decades, but it's a comedy club and it holds about 150 people. So we had most of it full to ourselves. And back then, they had a few stars in the group. They did different skits. And who was there? Well, some comedian called John Belushi, Dan Aykroyd, Gilda Radner, some of the great comedians that went on to start Saturday Night Live. And on Tuesday and Saturday shows, they were only at night, after the show, they take a break. We were at a Tuesday one, and they do improv. They come out and ask the crowd, give me the name of this or this or this, and people would yell out. We have 100 guys from a technical institute who are hell-bent on getting drunk, and we did. But anyways, we did yelled out some amazing things. And plus we were pretty rowdy, but they liked us. And next year we came back. And in the improv, the first skit didn't have anything to do with what we yelled out. It was a skit cutting the heck out of our fraternity. I mean, really good, but really cutting the heck out of us. And the next year we came back, they did the same thing. And my senior year, we came back and yeah, we got to meet those people afterward, but they cut the heck out of us. Well, a year or two after I graduated, a friend of mine who wasn't in a fraternity called me up and said, "Have you seen this movie, Animal House?" No. It's about fraternities and you were in a fraternity. So I went and saw it with some friends. And the opening scene, I said, wait a second, I've seen this before. And a couple other scenes. And it dawned on me, those were the skits that they did to cut us up. Now, the name of our fraternity was Alpha Epsilon Pi, but our nickname was the Apes, Animal House. And we had a guy who, I don't know why I remember his name because I haven't seen him in decades. His nickname was Yutz, who was the inspiration for Bluto, John Belushi's character. We didn't kill a horse, though. We never did that. But we had toga parties and we used to tell them about that. And Animal House is about ours. All right, now I got that out of the way. Let's get back to now the alpha hydrogen. I was talking about the Greek alphabet. Why did I get sidetracked? That's rare, but I think it was a fun sidetrack. Hope you enjoyed that. All right, the alpha hydrogens are acidic. And let's talk about it. The alpha hydrogens in a carbonyl compound, ketone or aldehyde, are more acidic than the hydrogens of an alkane. This is due to resonance stabilization of what's called the enolate anion. See board. Again, switches off, but now you're dealing with holy ground for Dr. White. These hydrogens are acidic, and this is an acid-base reaction. Now, why is the enolate anion? Because it's like the enol form, and I'll show you. This is called the enolate anion. Again, switches off. You don't have to write this down. Why is this very stable? Why does this happen? But if I had an alkane, that's never going to happen. That's because I can draw the following resonance structure. These electrons go here, these go here. And these two forms, resonance forms, the more you can draw of resonance forms, the more stable it is. And that makes the enolate anion more stable than this a negative charge on carbon. And that's why. Now, I shall tell you now that you've seen an enolate anion. My PhD thesis dealt with this very specialized enolate anion, and that was cross-conjugated, kinetically favored enolate anions. And I did chemistry with that. Now, let's look at the reaction I want to talk about. Now, enolate anions allow you to do something very special. What's very special? Making carbon-carbon single bonds. I'm only going to teach you one, but there are a number of ones I can show you. And this is called the aldol condensation. And the switch is on. Click, it's on. And the aldol condensation uses an enolate anion, which is a nucleophile like a Grignard that attacks carbonyls. Now, I'm going to do a special gift to you. Shh, don't tell anybody I'm being nice. And normally organic chemists wouldn't write it, but notice, and I'm going to stick to aldehydes. You can do this with ketones. I forgot to put the water here, some solvent. But if you take an aldehyde, and I have two of the same aldehyde in red and black, you'll form this compound. And this is called an aldol. Aldehyde, alcohol, aldol product. Now, let me show you what's happening, but first I'll let you copy that down. All right, let's go to the whiteboard and I'll show you a better way that my software doesn't like me to do. So I'm going to have to handwrite it. And my gift to you, if I put an aldol condensation reaction on the test, I'll write both aldehydes. And here, reacting with base, and I'm going to stick to sodium hydroxide for this class. There are many bases you could use. And the alpha carbon here forms the enolate anion that attacks that carbonyl carbon and opens it up to an alcohol, which is why you have the water present. And the first molecule, aldehyde, notice there's only one hydrogen here because I remove one of these to make the enolate anion. And then it's bonded to the other aldehyde. And what's attached to it is attached to it. So the key is making the enolate anion on the alpha carbon, and that attacks. Notice organic chemists are violent. We are. Be careful. No. But that attacks the carbonyl carbon of the other aldehyde. And that's the enolate, that's the aldol condensation. I'll do this one. If we look at this, ooh, two of the same aldehyde. That's a giveaway on my test. Oh, I gave it away. Shucks. But anyways, we're reacting the same aldehyde with sodium hydroxide and water. Look at the alpha carbon because I'm going to form the enolate anion. And I'm going to write that with one less. And I've already written the general reaction up here with one less hydrogen. That's the alpha carbon here. And that attacks this carbon here. I'm going to form a carbon-carbon single bond, something very special, very rare, and very powerful. This opens up to an alcohol, and all this stuff is still attached to it. And from a simple aldehyde, I've made a very, very complex molecule that I can do other things to make things with. And that's the aldol condensation. And that happens because of the enolate anion. All right, everybody have that written up. When you have finished writing it down, give me a thumbs up. All right. It's time for you to have fun with one. In fact, my last patent, I used a specialized version of this reaction to make a specialized thing called the resin, otherwise known as a glue, to hold sand together to help make molds to make V8 car engines. Which is not these molecules, but others. Your turn. Give the organic product or products for the following. And don't forget, commercial from Dr. White. If you have any questions, need any help whatsoever, tonight from 5 to 6:15 on Zoom, I will have my office hour. If you got any questions, come on by. Good news is you don't even have to get in your car or whatever to come to ECC. You can do it out of the comfort of your home or wherever. What was it? 2 semesters ago at another school, I was teaching a general chemistry class at my office hours, same time just about. And I had a student log in. I said, "What's all that noise?" "Oh, I'm in an ambulance." I said, "Are you all right?" "No, I work in an ambulance. I'm the driver, also a paramedic. We just dropped somebody off at the hospital and I got some free time. I figured I'd check in and ask you a question." And he was calling from the driver's seat on his iPad or whatever to me to log in. That was unusual. All right, everybody done? Not yet. All right, looks like everybody's done. All right, if we look at this, what's the first molecule? It's the same as the second one, and that's an aldehyde. Now you can do much more complex aldehydes and ketones actually have 2 alpha carbons, but I'm going to stick it simple. Oh, it's the second aldehyde is the same thing. And we're reacting it with base and water. And the alpha carbon will form the enolate anion. So I'll take off 1 hydrogen. And this will then attack this carbon, and I'll form a carbon-carbon single bond, opens it up to an alcohol. What's attached to it, CH2, R is still attached. What's R in this case? Methyl. So I'll have CH2, CH3, CH, take off 1 of the hydrogens from the alpha carbon. And I'll write the second. This right here is an alcohol. And then CH2 and my R group is CH3. And that's how you do the aldol condensation, which I've done. And I've done much more complex. They're called enolate anion reactions. And all of them, and this is the beauty of all of them, allow you to make carbon-carbon single bonds, something very rare, very special in life, in organic chemistry, in our world. Now, good news, it's time for a little gift for Dr. White. I will never put a synthesis problem on a test or a final using the aldol condensation. That truly would be cruel and unusual punishment. I don't do that. And if we look at the screen now, guess what? We're done with this chapter. We have finished the chapter on aldehydes and ketones. So as I always try and do, more than try, I always do, a week before any test, I have finished all the material that will be on test number 2. On Monday, I will do the practice problem set for aldehydes and ketones. If you have any questions, ask. On Monday, I will do my world famous review for the next test, test 2. And on Monday, we'll do some other stuff too. Any questions about aldehydes and ketones? I'm also looking at the chat, no pop-up. Well, in that case, guess what time it is? I had to sneak that in and did it again. It's time for lab. So let's have our lab, and you're going to get out early today. In real life, I would have lectured for only about an hour, but I knew I wanted to catch up. And sometimes even in face-to-face, I've done this. And now it's time for our lab. And today's lab deals with alcohols. And because they're flammable, I have that. If we were face-to-face, you'd be doing this. What's an alcohol? Carbon with a hydroxyl group. Alcohol. Oh, that reminds me, don't forget, hand in the lab that's due today, sometime today, please, if you haven't done that already. All right, now, one of the things that's important is the solubility of alcohols. And alcohols are soluble in water. Some of them are, maybe not, I'm lying to you. No. And because of hydrogen oxygen difference in electronegativities, this is lowercase delta, Greek letter also. I already told you the Animal House story. That was a fun time going there to Second City with a group like that. But anyways, there's a slight positive charge on hydrogen and a slight negative charge on oxygen. And water, the same thing happens. And because of Coulombic interactions, electrical attractions, opposites attract, there's a slight attraction called the hydrogen bond. Can I write it any smaller? And that's what makes water a liquid at room temperature. And this helps solubilize water and alcohol together. Now, does the length and how many carbons the R group has make a difference? Well, that's what you're going to figure out this lab. In this lab, you'll be turning to the solubility of water. And if we were face-to-face, what you would be doing is, in small test tubes, add enough deionized water. DI means deionized. We have filters at ECC that take certain ions like calcium and other things that are in your drinking water out, because that messes up this experiment. And you take a small test tube, fill it about a third with DI water, and each alcohol you're going to test, you put in a small amount, and then you mix it. We have vibro mixers, a plate hooked to motor. You push down, it goes real fast like that, mixes it. They're fun. Or if you didn't want to use that, let's assume this is a test tube. I'd tell you, hold it in one hand. And then 1, 2, 3, maybe 4, and that mixes it too real good. Never ever mix a test tube like this. I also tell students, don't tickle it, it won't mix it. You really got to hit it hard and hold it up. Well, no, this wasn't a test tube, but you got the message. And then after a minute or two, you look at the test tube, and if you see 2 layers, guess what? It's not soluble. If it's the same throughout, which we call homogeneous, it's soluble. Now, here are the alcohols. I've given you the actual results you would have gotten. Now, notice right here what I asked. Please draw right here for each alcohol the structure. If you don't, I'll take off a point. And that's the first part. The second part, I asked you to smell it And since you're not gonna go around smelling it, over the years, students have similar perceptions of what they smell, even though I'll talk later in the semester, one of the hardest problems I ever had to solve dealt with odor of a compound a company I worked for made. And if I didn't solve that, it would have cost the company about $60 million a year. And I was getting a call at 8 in the morning when I got to work, actually before that, when I got to work, also at noon and before I went home, from the president of the company in the United States. Did you solve it yet? It was not a fun time in my life. But odor problems and odor is very complex. And what I'd ask you to do is smell these. And I gave you different, what students have usually said it smells like. All right, let's move on. Let's talk about the oxidation of alcohols. Now, in this part, you'll investigate the oxidation of alcohols, what's called an oxidizing agent. That's acidic potassium dichromate. And this is used to determine, I'll talk about in a second, what type of alcohol you have. Do you have a primary or secondary alcohol, or do you have a tertiary alcohol? And let's look at the chemistry. We've done this, but in a more general way. Let me do something a little different here. You have a primary or secondary alcohol. Instead of using O in a bracket, what did I have? Potassium. Yep. And acid helps catalyze this reaction. And you have potassium dichromate solution. This is a red orange color, beautiful color. Dr. White likes reds. And what it will do, just like when you saw this, it will oxidize to either a ketone or aldehyde. When this is oxidized, this gets reduced, and you form chromium 3 plus ions, which, depending on the concentration, are either blue, blue-green, or green color. So if you see a color change, you have a primary, secondary alcohol. If you have a tertiary, well, yeah, if you have a tertiary alcohol, and you react it with potassium dichromate, you'll get no reaction. And also no color change. I'll give you time to catch up. Who is this thinking? Next chapter, we're going to talk about ketchup and mustard too. Bet you never thought I'd get into that in this class. I will. All right, so this is a very classic test. Before chemists had the electronic equipment we had, they used visual tests to tell if you have a primary, secondary alcohol or tertiary alcohol. In this case, what you'll do in a small test tube, you'll put 5, 10 drops of the alcohol, then about 10 drops of the very dilute aqueous acidic potassium dichromate. Then you'll mix the test tube as I showed you, and you'll put your observation in table 3. And because it's very acidic, we always wear eye protection. And I usually tell students, this is a good one to wear gloves, which ECC provides. I wear it during this lab. And if you notice, here are the different alcohols that are oxidized, and there's the results. Now, the last part is the reaction of alcohols with sodium metal. And this one I do myself. I never let students use the sodium metal. It's dangerous stuff to handle if you don't know how to handle it properly, which I do. And let's look at the following reaction. This is one that I'm doing in a lab, but we're not going to do in a test ever. And if you take an alcohol, I'm going to even balance it for you because sometimes students get upset when I don't. Sodium reacts with alcohols to make, and this is called an alkoxide, which I talked about in the Williamson ether synthesis. And yes, there's nomenclature, and that's the sodium alkoxide. And you get hydrogen gas. Now, it turns out alkoxides are very basic. If I can spell it. For those who forgot, we're talking about pH. And a quick refresher course. pH measures the acidity or basicity, or the amount of base or acid present. At pH 7, a solution is called neutral. At pH less than 7, it's acidic. And pH above 7, it's basic. If I have something at neutral pH and I add an acid, the pH will drop. If I have something that's at neutral pH, pH 7, and I add a base or create a base, the pH will increase. And what you're going to find out, if you were face-to-face, you'd watch, and I have pH paper, which changes color to indicate the pH, I would do the reaction and you would watch. And when I did it, you would see, now the hydrogen here is given off as a gas. And you would see bubbles. Oh, can I have one of those? I'm just kidding. And let's go back. And what I do is I make a solution of 2-propanol, which is an alcohol, and water, and measure the pH. It's 7. And then what I do is take 2-propanol, react it with sodium. You'll see bubbles, and put that in water, and now the pH is 13. And from that, you'll have to deduce, did I make an alkoxide? And was I telling you the truth about the basicity of alkoxides? And if we look, here are the various questions you need to answer. And with that, that's today's lab. Unfortunately, I don't have the experience of mixing things, but you get the same mental experience students face-to-face would interpreting the data. And with that, I'm done for today. Actually, for you people, excuse me, I'm getting all choked up over this, Cindy. Anyways, unless I see you tonight for my office hour, have a nice rest of the day, rest of the week, and I'll see you on Monday. With that, gehen gesund, be healthy. Bye now.